All right. So now we have got to module 2 of our machine learning class. And just to refresh your mind on what you studied in module 1, module 1 was more of a general introduction, or I call it a gentle introduction to machine learning. So we looked into the definition by various authors, taking a closer look at the definition by Tom Mitchell in terms of performance, task, and experience. We looked at concept learning, right? How you actually model a concept by using your find S and your candidate elimination algorithm, right? And then we also looked at some challenges or issues in machine learning, right? And obviously you also studied about the applications of machine learning in various fields. So, and you were able to answer some obvious questions, such as whether machine learning is overhyped and whether machine learning can solve all of humanity's problems. And we looked at the challenges that researchers face also in this field of study. And now you are all excited, to see what we have in store for you. So, and that leads us to module 2. So this is module 2, and in module 2, I want to do this in 2 parts. So module 2 is called decision tree learning. Decision tree learning. So by the way, you are able to implement, to understand 2 algorithms, right? Your finders and your candidate elimination. And here we'll be looking into another one, which we call the ID tree. Okay. So in decision tree learning, I want to divide this into 2 parts. So the first part, I'll prefer to call it section A. So in section A, we'll be looking into introduction to decision trees, introduction, followed by decision tree representations. So I will use decision tree representations, and subsequently you have appropriate problems for decision tree learning. Appropriate problems for DT3 learning. So section B will be in another class. Okay. Section. So now don't tell me section A is for A section students only and section B is for B section students only. Now what I'm trying to say is this, okay? So I'm going to split this into 2 lectures. So the first lecture series will look into introduction, how do you represent a decision tree, and appropriate problems for decision tree learning. So in section B, we take a classical example of your concept learning, which you also saw in your what? Candidate elimination lecture. All right. So in this case, so section B, I'm going to leave it for now. Let's dwell more on section A. So can we start here? So I will use this side. So we are now talking about this. Okay. So in introduction, what are we going to look at? You already know that decision tree is a family of what? It belongs to a family of what? Supervised learning algorithms, which we mostly use for what? Classification and regression based problems. So maybe I try writing something down here. So by way of intro, by way of introduction, we said that this is what? We take the keywords supervised. Okay. So solving what? Classification. classification, and what? Regression. 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 regression based problems. Then what else? So useful applications. Applications that has found useful application from what? Okay, so it has found useful applications in almost all fields of machine learning. In almost all fields. In almost all ML related tasks, such as diagnosis of medical conditions, diagnosis of medical conditions. So can you tell me quickly? So I'm talking generally about the applications of what? Decision trees only now, okay? Diagnosis of medical conditions. Then what else? Even to your class email spam classification. Email spam classification. Okay. So let's talk about credit risk prediction. Credit card risk prediction. Credit card risk prediction. So what exactly are we talking about here? Here we have either what we call our discrete. Okay, let me use the word now categorical first. Okay, so categorical, if you want to talk about diagnosis of disease, is it a categorical or a continuous variable? Obviously it's categorical. Okay, where we have presence of an ailment or a medical condition or absence of it, right? So if we want to diagnose whether someone has a skin cancer, okay, and either the skin cancer, here we say if it is malignant, that means there is presence of skin cancer. If it is benign, that means what? There is no skin cancer. So here we know that we are expecting a kind of a Boolean valued attribute, yes or no, right? True or false, which obviously you can one-hot encode into 1 or 0. Is that clear? So if we see that decision tree has its applications in diagnosis of medical condition, email spam classification. So we are asking the obvious question, is this a spam mail or not? Because you have already known what constitutes spam mails. So if it is spam, then put it in my junk mail. If it is in non-spam, let it enter into my inbox. So when we look at this, we know that we have what? Fixed labels. Whenever we are talking about classification, we can actually put a boundary, right? A decision boundary to the problem, such that easily the problem can be what? Easily separable, right? So you talk about credit card risk prediction, and we've seen this even in previous classes where we are talking about what? Whether a customer can, whether we can issue a credit card to a customer or not, or again whether a customer will pay back its debt or not. Okay, so if a bank wants to assess the risk of issuing a credit card to potential customers, so they should be able to look into the data, because we always believe that data don't lie. When you get the correct data, okay, after you have pre-processed it. So with that, you'll be able to predict whether the customer will pay back the loan or not. And remember, here we don't just look at one or two attributes. We have to consider so many things, right? So for example, can a bank issue a credit card to you students? The answer is no. Why? You are like a liability. You are not an asset to them. Why? Are you working? No. Okay, do you have an immovable property? Don't say my dad's property and stuff, okay? So because most times they will do what we call credit card risk assessment, okay, before they even issue a credit card. So that involves, they will want to know your paycheck, right? Your pay slip, sorry. And then they want to know how many years of experience do you have and stuff, and check whether you have defaulted also. Do you have, usually I think credit cards are given to holders of current accounts, okay? So there are instances, there are lots of situations where they really want to assess whether this customer is likely to default or not. So lots of data analytics goes into this, right? And based on that, they'll come up with a predictive model which you can actually say, okay, fine, this customer is liable to pay or not. So if you try to model this, say you are a risk assessment manager, that is the position you hold in the bank, say an SBI bank, and customer comes and you are meant to generate a kind of a classification. They won't tell you maybe it's a decision tree. They will ask you, you have been assigned, I beg your pardon, you have been assigned to come up with a model that will be able to assess the credit worthiness of what a customer. What will you look into? What will you look into? You might, for me, I will try to, okay, I don't know much about the technology in the bank. If you don't know, then you are not worthy to be a risk assessment manager. That's why, if you remember in our previous classes, okay, we said that you need to have what? A domain knowledge before you'll be able to apply what? Machine learning to a problem. Because if I don't know that I can model this with what? A decision tree, okay? Then, and I don't even know what terms what features or attributes I should look for. What features, let me use features now, that's most suited. What features I should look for when assessing the credit worthiness of what? A customer. So how am I even worthy to work in that bank, right? So basically they will look at, I think, the annual, maybe monthly income, and then see maybe what are the assets which you have, and maybe check whether you're a current account holder, and maybe again they will look into marital status, right? So maybe check some, lots of background work has to be done. We move to the next subsection, which is how do we represent a decision tree. So I'll call it DT representation. So I've given you hints actually. So how do you represent a decision tree? Okay, so we always start, representation of a decision tree. Pictorially, you have your root node, fine, which is your what? Primary point in which you decide how you start splitting the tree. The concepts here we have what? Nodes, N-O-D-E-S. Then you have your what? Splitting criteria or splitting condition. You have your pure nodes, right? Pure leaf nodes. So you start from here, and move down till you get here. So you stop. Whenever you get a pure leaf, that means you can no longer split. Then you know that you are done with that. So how do we put this in a refined way now? That decision trees are represented by always starting from the root node, okay, and then deciding on which one becomes your what, on whether the root should be split or not, okay. And then how do you decide the splitting criteria, and how do you traverse down? So if you to get to a pure leaf node, if the what data set is what unbiased, and we saw that in our inductive bias, right? Okay, in the previous class. So if in case you've forgotten, you can just get your mind refreshed by watching the video. So here we now say, okay, fine. Can we actually state the problems, okay, in which decision tree learning is appropriate? But before that, there is something I want you to note. So I hope you can see the board. I'll write here. So note that decision trees, and I will explain this. This is very important. Decision trees represents, okay, so I'll use one now. Decision tree represents a disjunction of conjunctions of some constraints on attribute values of instances, on attribute values of instances. Now, okay, let's define some terms here. What is disjunction? What is conjunction? How about an instance? What are attributes? So you can see some keywords here, right? So let's start from the one which you have seen before. You have seen, in fact, you have seen all actually from your first model. So we know attributes. So I will give equivalent attributes. Attributes refers to your what now? Columns, right? Fine. So an instance here represents your what? Rows. Okay? Now, another name for attributes can be what? Features. So if you remember from the concept of your whether I play tennis, okay, you saw it has about what? 5 attributes, right? So, or your what? Features, okay? Now, and there are instances, right? So there you checked how many rows there were there, about 14 of them, right? With positive instance, I think 9, and negative instance 5, right? So, now how about this conjunction now? Conjunctions. So in conjunction, we are talking about, it's similar to your AND operator. So AND operator. And you know, in AND operator, if you look at the truth table, you understand that only when both are true, that you get an output of true, right? Yes, 1 into 1. So if you look at it this way, so you have your inputs, high input, yes, and you got your outputs here, outputs here. So you can see conjunction as what? A multiplication, a multiplicative operation. Where just watch. Let's take the truth tables now. So it can bit off to 0, 0, 0, 1, 1, 0, 1, 1, right? So 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, 1 into 1 is 1. So this is what we are concerned about. So I will take a tree and then we model it as conjunctions and disjunctions based on what? Attribute value pair. Usually an attribute goes to your with value. You remember the concept of dictionary in Python? Yes, attribute value pair, right? So you see attribute value pair based on disjunctions or conjunctions. So we will look into a conjunction first, okay, internally, and then disjunction, because every tree usually is what? Every tree is what? A disjunction of conjunctions, right? So we will take example and you see. So now you look at your disjunction then. In disjunction, disjunction is equivalent to what? An OR operator. So OR is like additive operator, right? So in OR, all I want is the only condition is when you have both inputs at 0, as 0, then only you get 0. Otherwise you get 1. And if you look at the truth table of your OR gate, it looks like this. Again, I'm taking inputs, and I'll take an output here, So if I start again 0, 0, 0, 1, 1, 0, 1, 1, you see 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. So you see in all these cases, only when both are 0, you will get only an output of 0. So what are we saying now? Let's take example of a tree to illustrate the concept of what? Disjunction and conjunctions based on attribute value pair. So 1 minute, I'll wipe this bird. So I hope so far you are able to follow, right? So let's get there. Now, so the tree might not be exactly, okay, but yeah, let's try to see if we can actually model this. So the first one, so we take a representative example, a representative example of what? Disjunction of conjunctions of what? Attribute value pair. So this is the tree we are going to get to when we take our what? When we model a decision tree problem based on ID tree algorithm. But let's just look at this based on disjunctions and conjunctions. So we saw that sunny there, and then we checked humidity as well. Humidity. And then if it is high, it was what? No here. And then if it was normal here, normal, then it was yes there. Now, and we saw overcast, it was yes. And the other left, rightmost part of the tree, we saw rainy or rain. And then we looked at wind again. And then if the wind was strong, if we had a strong wind, we negate it, say no. Otherwise, yes. So can we represent these three as what? Disjunctions and conjunctions based on the attribute value pair? Yes. So now you follow along. Here, we start, remember, we always start from, I just wiped it now. We always start from the what? Root node, right? And traverse this till we get here. So why don't we label this now? So Outlook is my root node. Don't worry, we will look into why we decided, how we decided that Outlook is the root node, okay? So root node, we will look into that later. So this was my splitting criteria, okay? Okay, so here, now here is my pure leaf node, pure, because there was no further splitting here, pure leaf. And all these ones, 1, 2, 3, 4, all these are again my pure leaves, right? So these are all my pure leaves. Okay, so let's move down this way. Look for the one that will give us a positive outcome quickly. So you start from root node, Outlook, okay, then sunny, then humidity, then normal, till you get here, right? Yes. Then comes your disjunction, or. This is yes. Again, or, okay? So you take this rain, wind, and weak, right? Yes. So we will have how many? So this one yes, another yes, and the last yes. So I will use this space for it now. So starting from the root node, what will it be? Quickly. Outlook equals sunny, so I'm writing here. So Outlook equals what? Sunny. Okay. Now, what do you think will come next? Outlook equals sunny and, right? I told you first we consider our conjunctions. So and, now and is represented with this symbol, okay? It's called the carat symbol, right? So and humidity, don't call it humidity, okay? Humidity equals what? Normal. Okay? So that gave us what? A true instance, right? Yes. Yes. Sorry, a pure outcome, right? Yes. So after this, we now move into what? Disjunction. So which is or. What is the next thing there? Quickly. Outlook equal what? Overcast, right? Outlook equal what? Overcast. Or Outlook equal what? Overcast. Overcast. Then or. What's the last one? What's the last one? So you see Outlook equal rain, okay? Outlook equal rain, then and wind equal weak, right? Fine. So we do that now. Or Outlook equal rain. Now or and, please. That is conjunction, okay? Whenever I say and, remember it's conjunction. And wind equal what? Weak. So I'm going to highlight this is my disjunction. Oh yeah, another disjunction of what? Conjunctions. Now you see disjunction of conjunctions. Okay, fine. Disjunctions of conjunctions. So this represents what? The expression in terms of conjunctions and disjunctions. I hope you got my point. So I will repeat once more that when you want to represent a decision tree in terms of disjunctions of conjunctions, that you need to understand that conjunction purely mirrors your AND operator. And I just explained to you that AND operator is only a positive. I mean, you get a yes or a true condition when both of them are true. Otherwise, it's false. And again, your disjunction represents your OR condition, right? So either true or false in both cases, except when both are false, right? So we look at it first by going internally and then externally. So I don't want to say internally, externally, say inwardly, we traverse inwardly. That means going from here to all the conditions that were yes conditions, right? So we didn't consider the negations, okay? So here we started from the root, okay? And then this was our splitting criteria, and then we moved down to this where we got the pure leaves. There's no further splitting. So these three we will generate in the subsequent lecture, okay? So here we got the outlook equals sunny, and because we are talking about conjunction, humidity equal normal was yes, or outlook equal overcast, or outlook equal what? Rain, and wind equal weak. Fine. So we are done with this, and before we move into a classical example of taking our concept learning problem and modeling it to get the decision tree, I want to summarize the class. So what have we studied? So what have we learned so far? We started by introducing the concepts of decision trees, right? Taking a closer look at what? The definition of a decision tree. We said something that decision tree belongs to the class of what? Supervised learning algorithms for solving what? Yeah, complete it. For solving what? Clustering problem. Okay. For solving problems that are based on classification and regression, right? So that, and we know that almost every problem can be modeled using a decision tree. And we also looked into what? Practical applications of decision tree, okay? Ranging from what? Medical diagnosis to your what? Even credit card risk prediction, okay? And we saw how you can represent what? A decision tree. That usually we classify it starting from the instance that it traverses, moves down in a top-down approach. Starting from the root to the pure leaf where there is no further splitting. After that, we looked into what? Appropriate problems for decision tree learning. So this I have not explained, it's just some notes, okay? So the appropriate problems for decision tree learning is asking us the question, what are the problems which we can represent using a decision tree? So what are the problems? Can you just give me any insights? So the first problem is what? What are the problems that is appropriate? Did I say problems? Yes. So what are the problems that is appropriate for what? Decision tree learning. So the first one is what? Problems that have what? Attribute value pair. So I won't call it problem now because you think we are generating some problems, right? So I will say instances that are represented by attribute value pair. And I'll take this for example from here, okay? So instances that are represented by attributes value pair. Actually, I explained this before, but yes, by way of writing down, let's get. So can you tell me the attribute there and the value? So attributes in the table can be see temperature and then the value hot, cold, mild, okay? So example, so temp is my attribute, okay? Temperature is my attribute. I'm using attribute for short, okay? Okay, let me write it in full. Attribute, and the value can be what now? Hot, cold, mild. Value, hot, cold, mild, okay? So remember I told you even in your Python class, you can model it as attributes, temp, colon, hot, right? As a dictionary, right? So that is the first one. The second one, so it works well, works when target function has what? Can you complete it? Has what? Discrete output values. Has discrete output values. So can you give me an example now from the table, from the figure we have seen? Can you give me an example? So here we are talking about what? See there, you can see, right? It's a Boolean, right? A Boolean. Okay, it depends on how you call it, Boolean or Boolean anyway. It's a Boolean function, Boolean, such as yes or no. Can we represent it as true or false? Why not? 1 and 0? Why not? Okay. Now, write it here. Disjunctions and conjunctions. Disjunctions and conjunctions. Then I will explain the other ones. And then the fourth one, if it what? If it what? If it does not contain error. Okay. Okay. So see, we say may or may not contain error. May not contain error. Then I will explain. May not contain, where the instances do may not contain error. May not, remember it can contain, okay? And then where there are no missing values. Think, no? Think. So if we say there are no missing values, then you are wrong, right? Because in our inductive bias, right? Yeah, we were not able to converge to a solution because of what? The instances doesn't have a unique word solution. That means it was biased. So here again, the appropriate word, if you permit me, I'll say may not contain missing values. May not contain missing values. So these missing values we will explain. Now till here, see, the only thing that might be new to you is containing error and missing value, right? Because if you look at that table, you're able to draw the conclusion that instances that are represented by attribute value pair, you've seen that. Conjunctions or disjunctions, you've seen that. Works on when we have discrete output, you've seen it, right? Now, may or may not contain error, because if you look at this table, the figure, I keep saying table, why? If you look at the figure, you will see that we are able to get a decision tree because our data set was not biased. What was given was not biased. But since I said splitting and splitting, so this has only two levels, right? Level 1 and level 2, and we are done with this. So in classical, in real-world scenario, you might even get to the 5th or 6th or 7th level. At that stage, you see, you have even lost that homogeneity. You don't even know when this is going to stop splitting, right? So the best way is to decide how many levels you want the tree to have. Prefix it before, okay, and stop when it didn't reach that level, right? So, or you can also do pruning, okay? That is not possible in ID tree, okay? So basically, if it contains error, you might not arrive at the pure leaf, and you keep splitting to eternity. Now, how about when you have missing values? So what can be said to be what might be the missing values here? So can we have an entire row that is missing? In most cases, instances cannot be missing entirely, right? Because if it's missing, you don't know, right? You don't know what, you don't even know that is there. If the entire row, I'm talking about if the entire row, think of this. One student's record is missing completely. That means the student never appeared for any exam at all. Only the name is there, but no exam, nothing. How will you generate marks, right? So the best approach to that situation is to drop the entire row, right? Now, but that barely happens. So what usually happens is you have few attributes or features that are missing. So there are different ways in which you can overcome this problem. And in real life, maybe we use what we call imputation method, where you might use the model imputation, where you consider only the model value, the one that has the highest, the one that occurs more frequently. Say this student was getting around 75, 80, 85, 90. So you might say, okay, fine, the person got 85 twice, so maybe in ML, this person is likely to get 85. Or you use the mean value, right? Add everything up, the five subject scores which you have, and then you divide by 5, right? So in most cases, you might also take the median value also. Or basically we try to say, okay, fine, let's approximate this and maybe I give the student, yeah, in between the person is likely to get between 85 and 90. So these are the practical situations, okay, the practical solutions to this problem of what handling missing values. But in your syllabus so far, okay, this table doesn't have any missing what? Value. So you are safe, okay? But I would like you to look into a practical situation where you got what? Missing values. And with that, we wind up for today. And then in the next class, we start with what? Computing this decision tree. Thank you.